Hi everyone. We are going to dig into this idea of limits a little bit more deeply in section 1.3. I introduced it in 1.2, but now we're getting into the formal definition of a limit, left and right limits, and a little bit about this idea of continuity. So, our formal definition is the following. When we write the limit as x approaches a of f of x is equal to L, that means as f of x gets closer and closer to L as x gets closer and closer to A. But x doesn't have to ever get to A. So we can take a look at limits graphically, numerically, and algebraically, as you saw in section 1.2. An example of a graphical limit right here. If we were interested, we might want to know that the graph tells us that the limit exists as x approaches 1. And how do we know that? Well, first of all, we're interested in the limit as x approaches 1 of the function x cubed minus 1 over x minus 1. Below is a graph of that, and what you will see as x approaches 1, which you may or may not be able to tell from this graph, as x approaches 1 from the left and the right, y, or f of x, approaches a value of 3. We could also take a look at that same limit using a table of values, and we would want to take a look at what happens as x is approaching 1 from below or from the left, and as x is approaching 1 from above the right. And this is where that definition is really important. It says above is that we know that f of x gets arbitrarily close to some limit L as x gets close to but not equal to A. So, in other words, you can't really see it in the graph, but in this table, we're interested in the limit as x approaches 1, but at x equal 1, the function does not exist. However, as x approaches 1 from the left, f of x or y appears to be approaching 3. As x approaches 1 from the right, f of x or y appears to be approaching 3, which is what we see on the graph as well. What we can't see on the graph is that the function doesn't exist at x equal 1. Now, you may or may not have thought about that. The reason it does not exist at x equal 1 is because if you put 1 in for x, you get a denominator of 0, and you cannot divide by 0. It's undefined. And then finally, we can approach this one algebraically. And if you approach this one algebraically, basically what you would do is you would factor this cubic in the numerator, and it factors into x minus 1 times x squared plus 1 plus 1, x squared plus x plus 1 over x minus 1, and algebraically these two cancel out, and one of the rules of limits is try substitution. So at this point, if we tried substitution, we would get 1 squared, which is 1, plus 1 plus 1, which is 3. If we had tried substitution to begin with, our denominator would have been 0, and we could not evaluate that. So we're going to take a look at graphical, numerical, and algebraic representations of limits. Before we go any further, what we want to do is we want to talk about left and right limits. And I alluded to that in the graph above and in the table above, but not the algebraic example above. And so here's what that left and right limit thing is important, why that is important. We can say that the limit as x approaches c of f of x is equal to L as long as the following two things are true. As long as when we approach c from below, that's what that little negative means there, the limit of f of x is L. And, this is really important, and when we approach c from above, that's what that little positive is there, the limit of f of x is also equal to L. So in summary, if the left and right limits are equal, then the limit exists as x approaches c. So to relate that back to the graph, you can see as we approached x equal 1 from the left and the right, let me highlight that, from the left and from the right in blue, the y values, or f of x, approached 3. So the left and right limits were equal, so the limit as x approaches 1 is equal to 3. The same thing was true for the tables. As we approached from the left in green, we saw that y approached 3. As we approach from the right in blue, we see that y approached 3. So the left and right limits were both equal to 3. So even though the function doesn't exist at x equal 1, the limit does exist. So we are going to do a little practice at this point. And we're going to take a look at various limits of f of x. The first one as x approaches 0 from the positive direction. The second one as x approaches 0 from the negative direction. And the third one as x approaches 0. So the first one is the right-hand limit. The second one is a left-hand limit. And the third one is just called the limit. So let's take a look and see what we get. So as x approaches 0 from the positive direction, y is approaching 0. As x approaches 0 from the left-hand side, y is approaching -1. And therefore, since the left and right limits are not equal, then this limit as x approaches 0 does not exist, even though the left and right limits do exist. So we can say that the limit as x approaches 0 from the positive direction is 0. The limit as x approaches 0 from the negative direction is -1, and therefore those limits are not equal. The limit as x approaches 0 therefore does not exist. So here's what I'd like you to do. I'd like you to pause the video and try the rest of these limits, and then unpause the video and take a look at the answers. Okay, so let's go over these. The limit as x approaches 1 from the positive direction. What is f of x approaching? It's approaching 2. As x approaches 1 from the left-hand direction, it's approaching 2. Even though f of 1 is not equal to 2, the limit is equal to 2. As x approaches -1 from the positive direction, so that is like that, y is approaching 0, or f of x is approaching 0. As x is approaching -1 from the negative direction, well, the graph doesn't exist to the left of -1. The function doesn't exist there, so you can't talk about a limit because there's no part of the graph to be on to approach x equal -1 from the left-hand side. So the limit as x approaches -1 from the left, from the negative side, does not exist. Therefore, the limit as x approaches -1 does not exist because these two limits right here are not equal to each other. The limit as x approaches 2 from the positive direction approaches 0. As x approaches 2 from the negative direction approaches 0. Both of those are equal, so the limit as x approaches 2 is 0. And then finally, you might not think about it, but basically, if we think of the point right here at x equal 2.5 as x approaches 2.5 from the positive direction, y approaches 0, basically stays at 0. As x approaches 2.5 from the negative direction, y stays at 0. We could say it approaches 0, and therefore the limit as x approaches 2.5 is equal to 0. In the next part of this activity, you're going to work on Desmos and find some limits graphically, which I think is one of the easier ways to do it. So we'll start with the first one. The limit as x approaches 0 of sine of ax over ax, where a is a positive integer. So what I will show you here is I picked 3 for the value of a, and if I get a graph of that, I will see that as x approaches 0, y, or f of x, approaches 1 from the left and the right, so that limit is equal to 1. So let's go down and fill that in. This is equal to 1. What I would like you to do at this point is pause the video and use Desmos to find the corresponding limits. Then unpause the video and check your answers. Alright, so here are those limits. Take a look at those and go back and try them again if you did not get the same answers that I did. This is not the end of section 1.3, but we're going to stop here and we'll pick up with the rest of it in the next lesson.